Hello, my name is Grzegorz Rajchel Mieldzioc, and I'd like to tell you about our research called 36 Entangled Officers of Euler and resulting quantum error correcting code. Let me start by a motivation. So, the main motivation for our work was to connect two seemingly very distant regions of science, which is quantum information and combinatorics. Specifically, we were interested whether combinatorial designs can help us in quantum information. For the rest of my talk, I'll try to convince you that this is indeed so. Let me start by toy combinatorial model. Suppose you are given 4 cards, 2 aces of different suits and 2 kings of different suits, equivalently to letters, to Roman letters and to Greek letters. Can you reorder them so that each row and column includes both ranks and suits? Such an arrangement would be called Greco-Latin square. So suppose you put ace of spades in the left upper corner. Now, right upper corner must be king of diamonds. However, the same king of diamonds should be put in the left bottom corner. So it occurs that there are no Greco-Latin squares of size 2. Similar case in the higher dimensions, however, has solutions. So what you can see on the slide is a solution to Greco-Latin squares of size 3. There exist also Greco-Latin squares of size 4, 5, 7, and so on. Note that I omitted case 6. Why is that? It was already Euler in the late 18th century who discovered that it is not easy to find arrangement of 36 officers of different ranks and suits. Now, he was not able to prove that it is impossible to find such an arrangement. However, he posed this as a conjecture. The problem was not really easy, since even Euler was not able to find it, but it was proven 121 years later by French mathematician Gaston Terry. What you see on the slide is an approximate solution to the problem. So since there is no solution, can you see why this is only an approximate solution? I encourage you to pause the video. Okay, I hope everyone was able to find it. In the 2 last columns, the suits are the same. So this is only an approximate solution, not a really, truly in Greco-Latin square. How does this connect with entanglement? So every Greco-Latin square leads to an AME, absolutely maximally entangled states of 4 subsystems. What do we mean by an AME state? AME state is such that any possible splittings into 2 subsystems yields a state with maximal entanglement. How do we construct them from Greco-Latin squares? It is simple construction by taking each row and the position of each element denotes the state on the first 2 subsystems, and the card denotes the last 2 subsystems. Then we sum up all these elements and we obtain AME state, for which mathematical formula is below. Existence of AME states is not easy to check. So it is known that in many local dimensions and number of parties, these states exist. And it is known that for some of them, it does not exist. However, some cases are open. The smallest case that is open is case of 4 Q-hexes. So 4 subsystems, 6 levels each. And as of the beginning of this year, it is not known whether there exists such an AME state or if it does not exist. I'm happy to announce the main result of our work, which is that absolutely maximally entangled state of 4 Q-hexes do exist. What you see on this slide is quantum Greco-Latin square, which is different from the classical one by the entanglement of each element. So each card is entangled with some other card. So I'd like to tell you how did we get to this solution. So we started by some numerical procedures. In order to find numerical solution, we must find a goal function. So we've chosen entangling power, which is defined for a state or equivalently for a matrix connected with a state as a sum of linear entropies of a matrix, matrix with a swap, and the swap itself. The complementary notion is gate typicality, which says how typical a given matrix is. And now, a matrix is 2 unitary, or the state is AME, if and only if its entangling power equals 1. So this is maximal value. As you can see, the close-up of a region of interest, at the beginning we were able to get pretty close, starting from the approximate classical solution, which is presented in here. And this approximate classical solution has entangling power almost equal to 1. However, it's only almost. Now, the important fact was the particular choice of an algorithm. So the successful algorithm turned out to be the one which takes matrix, reshuffles it, then applies partial transposition, and then projects it back into unitary matrices with polar decomposition. One may wonder what should be the seed for this algorithm, because not all matrices, in fact, very few of them, do converge to an AME state or to unitary matrix. In fact, if we take this closest classical approximation, then if we apply iteratively this algorithm, we are not able to go into 1. Even if we perturb it by a small random matrix, it is still not going to give us 1. However, it turns out that if we take slightly different, slightly farther away from the solution matrix, which is PS, which is farther from P, then if we perturb it, we are really able to get 1. The convergence of the algorithm is shown in here. As you can see, it's pretty good. Now, the problem with this solution that we got is that even though there are a lot of zeros in our matrix, the rest of the elements are only numerical values, which means that not only it's not simple to present it in a readable form, but also it does not really prove that this is AME. We need to have analytical formula. In order to obtain it, we applied rotations on local subsystems. By such rotations, we do not change entanglement, which is good for us, but we are able to clean up the numerical values. So instead of over 400 numerical values, we obtained a little above 100 analytical values. Well, 100 does not seem like a small number. However, there is only 3 distinct values with a phase. So these 3 distinct values I presented in here, it's A, B, and C with phase omega. Now, not only this is analytical form, but also these values form a famous golden ratio. So it is not, the connection goes deep not only to Euler, but also to Greeks. If you want to check our solution, you're encouraged to do so. In the lower part of a slide, I present the link necessary to do that. Okay, so now I'd like to move on to applications of our solution. I'd like to tell you specifically about error correcting codes. In order to talk about quantum error correcting codes, I'd like to start with classical idea that might be useful, but is not useful after all. So classically, we propose that we can set up a code which employs redundancy. So we clone our message, for example, 0 into 3 zeros. Then if there is only one error, we still can go back to the original message. However, similar thing is not possible in the quantum domain since the famous non-cloning theorem. So quantum error correcting codes are or detecting codes which differ from each other, because correcting means that we are able to correct an error, and detecting means that we are only able to detect that the error occurred, but not necessarily to correct it. So these codes are employed by entanglement. However, there's a not very good thing for us, which is that the usual technique for correcting correction codes is that a stabilizer, which is the usual technique, works only for certain dimensions and error numbers. So it is useful to find also new codes which will work for different dimensions and error numbers. So I'm happy to announce that our solution, our Ahmad state provides us with a construction of encoding one QHEX, which is state with 6 internal levels, into 3 QHEXs with distance 2, which means that this is a detecting code. How do we do this? So each level is encoded into each row of our quantum Greco-Latin square. Note that since our Greco-Latin square is entangled, then the terms of the code are also entangled. To sum up, we were able to find a solution to the quantum Euler problem, and there's also a funny numerology. So Gast and Terry proved that there is no solution to the classical Euler problem 121 years after Euler posed the problem, and 121 year after Gast and Terry, we prove that there is indeed a quantum solution. Our Ahmad state provides us with new nonlinear QHEX quantum error detecting code, which might be particularly useful for transmission of the results of a dice game. Thank you for your attention.